Okay, hi everyone. Today's lecture is going to be on the continuous time Fourier transform. I'll give you a quick outline of what we're going to cover. First, I'm going to give you the definition of the continuous time Fourier transform. And second, I'm going to give you an example on how to calculate it. All right, so we'll start with the definition. Given a continuous time signal x of t, the continuous time Fourier transform x of omega is defined as follows. Any questions about my notation? All right. So that's the definition of a Fourier transform. The next part, we're going to give you an example how to compute it. So here's my example. Let's say we have this continuous time signal here. Now we want to compute the Fourier transform of this. So we plug it right into our definition here. We get this. When we look at, we're integrating over time, right? The support of this function is only from negative t to t. So that's what we're going to put in our integral. And the amplitude of x of t over its support is always 1. So we can ignore that, assign it to 1, and we just get this. This is an integral from calculus, which we can evaluate to get this. With these limits. And if you evaluate this, you'll get this. Well, we're going to have to use something called Euler's identity. Does anyone recall Euler's identity? What is this equal to? In terms of sine and cosine. Anyone remember?
It's cosine of theta plus j sine of theta.
Okay. Yeah, so we're going to use Euler's identity here to help simplify this. So let's show how we do that. So our first we get, first we're going to have this. Right, from calculus. Then we're going to use Euler's identity to simplify this part. So we get this. Cosine omega t minus j sine omega t minus cosine. Can everyone see this? Is it too small? Well, hopefully you can see it. Cosine omega t plus j sine omega t. And this simplifies. What cancels here? Cosines cancel. And we get 2 of the j sine terms. So we get 1 over minus j omega times 2 of minus 2j sine omega t. Here we get another cancellation of our minus j. So out of this we get 2 sine omega t over omega. And this has a special name. Anyone know what it's called? Sinc function. All right, so this is a sinc function. And we can plot this if we want. I'll plot it right here. The tricky thing about this is when omega equals 0, we plug in 0 and we get 0 over 0. Right here, sine of omega equal to 0. We get 0 over 0. Some people don't know what to do. What do? We do something from calculus. Anyone remember? L'Hopital is take the derivative of the top and the bottom, and that's equivalent as we take the limit of this. So what's the derivative of the top? We get 2t cosine omega t. Oops. Cosine omega t divided by 1. So we're trying to evaluate x of omega when omega goes to 0. And we use L'Hopital. Here, we get this. And from this, we get 2t. So that gives us this value here. It's equal to 2t. And then since it's a sine function, we know when it's equal to 0, which is at 2t, or 2 pi over t. Oh, sorry. Pi over t, 2 pi over t, 3 pi over t, and so on. And this is minus pi over t, minus 2 pi over t, so on. And our function looks like this. And it decays linearly because of this omega in the denominator right there. So it looks like that. So that here is our answer. This is a Fourier transform of this function here, as we just calculated it with our definition. So are there any questions? All right, that's it. Thank you.